Um, so, yes, welcome everybody. A great pleasure to have Andy speak to us again. Spoke to us a couple of years ago now, I guess, on National Schools Observatory. But I knew he'd done this talk to a local astronomical society here, the Southport Society, which we have links with. As you know, they helped to ship the telescope from the UK for use by ASB just before the pandemic, I think. But anyway, Andy, I've known for many years as a colleague of mine at Liverpool John Moores University, but he did his first degree in computational physics at Warwick, then went to do a PhD in astronomy with the title of Mapping the Large-Scale Structure of the Universe at Glasgow. So nothing too tricky there. And I did a postdoc at Southampton. Then I was delighted when he joined JMU in 1998, crikey, when we're all lads, and became the director of the National Schools Observatory. After that, ultimately became Professor of Education and Engagement, first of its kind, certainly at JMU, and was also, I think this was the title, the National Astronomer, was it, Andy, when you travelled the country by?
No, I was Space Ambassador for the Northwest of England and Shropshire.
Oh, okay, right. But didn't you travel the country under an STFC or?
Oh yes, no, just yes. They didn't have an official title for that.
Oh, one. Okay. Yeah, but you did thousands of miles by rail, including going to Scottish Islands and remote parts of the UK, all the way from the north to south, east to west.
Still recovering.
Yes, I doubt whether you could do it by rail now, to be honest. It'd take you twice as long anyway. Okay, so without further ado, I'll hand over to Andy to talk about astronomy and art, universal appeal. Thank you, Andy.
Thank you, Mike, and thank you everybody else, and thank you, Harold. I'm getting a bit of hemisphere envy at the moment. It's nowhere near as nice up here. So yes, thank you everyone for joining. This is a little bit different from the kind of things I normally talk about, but over the last probably 15, 20 years, I've gradually got more interested in the overlap between science and art, and in particular astronomy and art. And that's led me to doing some quite unusual things with artists of various kinds. And it's quite interesting to share it, and to share what I've learned from doing that. See if I can get this thing to move forward. Come on. There we go. So I'm going to start by actually trying to put this into a reasonably recent historical context. Back in the late 50s and early 60s, the UK government commissioned a report, as governments do when they don't want to actually do anything. And they commissioned Sir Charles Snow, CP Snow, to look at what they called the two cultures, sciences and the arts, and to come up with a report which looked at possible connections between the two, but also where they weren't matching, where they weren't working together and potentially could do. And there were some very interesting aspects to this report. He called it the two cultures because he felt they were separate. There wasn't very much overlap between the two. There was sometimes even disagreement between the two areas, between the arts and the sciences. And there are a few quotes in this report which I think have a little bit of relevance even today, whatever it is, 60 years later. This is a particularly important one. He said that, "I believe that if you'd asked a simple question, such as what do you mean by mass or acceleration, which is the scientific equivalent of saying, can you read, not more than 1 in 10 of the highly educated would have felt that I was speaking the same language." So he's basically saying that when he did this report, there was a feeling that the arts was something that everybody should know, but the sciences were something that only scientists needed to care about. That may have been almost true in the late 50s. It's certainly not true now. But there is still, popularly, a very strong separation between the two. If you put the word science into Google and just take the words that come out of it and put it in a word cloud, you end up with things like this. The common words that have come up are things like formal, natural, study. Universe comes in there quite a lot, but they're quite hard sort of words. Whereas if you put art in, you get things like creation, human, skill, decorative. And so the way people talk about these two areas are very different, and they are different in many ways. But I'm interested in seeing whether there's ways in which they overlap and whether there's ways in which they can support each other. So in this particular talk, I'm going to look at three different ways in which science and art can work together. Initially, science helping art, science making, allowing artists to do things that they wouldn't otherwise be able to do. I'm then looking a little bit about the possibility of art helping science in the same way. Art and artists allowing scientists to do things that they otherwise wouldn't be able to do. And then I'm going to finish off with something which I don't really think there's a word for yet, but it's not art helping science or science helping art, but the two of them coming together to create something which is different from both. I'm just calling that culture for want of a better word, but it's not something that we come across very often, this kind of completely even mix between the arts and the sciences coming together to try and create something genuinely new. But I'm going to start with science helping art. This picture in the background is a fairly classic example. This is a lovely painting by Joseph Wright of Derby. I love his paintings. I love the way he uses light. But this is a painting of a traveling scientist. Wasn't really a scientist. He was a performer, but traveling around the country with the newly invented air pump. And you can see the air pump at the top there with a bird in it. And these people travel around the country with these newly invented air pumps, and they would set them up and they'd put birds in them and they'd pump the air out and the bird would fall unconscious. And you can see the children at the bottom there are quite upset by this. And then if the demonstrator was good at exactly the right moment, they'd let the air back in and the bird would revive and everybody would be happy. And if they weren't very good, they'd leave it slightly too long and the bird wouldn't revive. And that would be a little bit disturbing for everybody. But it was the beginnings of science as a performance. But the connection between science and art and science helping art came about long before that. It probably goes back as far as art does. But there are some very specific examples which are worth highlighting because they're not showcased by the arts, but they have made art that is different. They've changed the way art works. A very good example of this is the use of the camera obscura, a simple optical device to project a real scene onto a flat surface. And artists have been using the camera obscura to help with their painting for a long time, certainly since the Renaissance and probably before. Hockney is very passionate about this. He's written a very good book called Secret Knowledge, where he looks for evidence that artists were using camera obscuras far before the art history establishment thinks was the case. And here you've got an example of this happening. You've got the scene that's being painted outside the artist's portable box. There's a small lens in the side of the box. Inside the box, it's dark, and you've got the artist, and the image is projected upside down onto the canvas, and the artist can then sketch around it and paint it. And this essentially just means they can work faster. And if you're an artist in the Renaissance, the more paintings you produce, the more chance you have of having enough money to eat. It's very simple. So anything that makes their life easier is important. And there's evidence for this even in paintings where the art history establishment sort of assumes it wasn't happening. This is a good example. This is a lovely painting by Lorenzo Lotto from 1523 of a husband and wife. And it's a nice picture of the two of them there. And he's, there's all sorts of meanings in the scene in the background, and the dog and the piece of paper and so on. But I'm not interested in any of that. I'm interested in the cloth. Because if you look at this cloth, it's a very nice example of perspective, which always had to include in paintings of this period. But actually, if you look really closely, the perspective isn't right. If you look at this little pattern on the cloth, for example, and you take the perspective at the front of the cloth, which is these blue lines, and you take those back, those lines will all meet at a vanishing point, well off the canvas, but they meet at a vanishing point, which is how perspective works. But if you look at the back of the pattern, where you've got the green lines, those lines disappear off, but they meet at a different vanishing point, which is not how perspective should work. There should only be a single vanishing point for this thing. However, if you're creating this with an old camera obscura, you do have a slight problem in that the optics are not brilliant. The lenses tend to be very small, and so you don't get a very good depth of field. So you can set up your camera obscura so that it focuses on the front of this cloth, but anything past the front will be out of focus. So what you do is you set it up and you sketch out the front of the cloth, and then you adjust your focus. You adjust your camera obscura so that the latter part, the back part of the pattern is in focus, and then you sketch that one in. It's all fine. But when you change that focus, you change where the perspective comes together in exactly the way that you see here. So this is exactly what you would expect if Lotto was using a camera obscura. It's not conclusive proof, but there's a lot of evidence here that people like Lotto were using these camera obscuras early on to help them produce the best art that they could as quickly as possible. And they didn't go around advertising the fact, because why would they? But it almost certainly was happening. But there are other instances of this which are perhaps more subtle, but in many ways perhaps more important. And a good example of this is the paintings of Turner, really one of the most famous European artists of his period. And this is an early watercolor by Turner. It's of a waterfall on the Clyde, and it's a very good watercolor, but it's a fairly classic watercolor of its time. You can see that the paint has been put on in splodges with quite firm edges. There's not much blurring together of the paints. But not long after Turner did this painting, he created one that looks more like this. This is a painting of Lake Lucerne, now in the Courtauld Institute, and it's quite different. And one of the reasons it's quite different is you don't have so many of those clear edges to the paint. You've got blurring together. And that may well be because this was done on a new kind of paper. Between that first watercolor and this one, a new kind of paper had been developed and put on the market. And it was different in that you could get it really wet without it falling apart. Prior to that paper, you couldn't get your paper really soggy or it would just disintegrate. But this new paper came along where you could get it very soggy and it would stay soggy. And that meant that you could put watercolors on and they would spread and they would blur and you could mix them together on the paper, which hadn't been possible before. And there's a paper historian called Peter Bauer who argues that without this new paper, Turner would not have been able to produce these paintings. And therefore, the paper allowed him to produce a different kind of art. And at about the same time as he was switching over from these, if you like, more traditional watercolors to the more flowing ones, he was doing the same sort of things in his oils, the much more famous paintings. And so suddenly in his oil paintings, you get this blurring together, which he wasn't really doing quite so much before that. So Peter Bauer has argued that without that change in paper, without the technology to produce that new paper, we wouldn't have paintings like Slave Ship, one of the most famous paintings that Turner ever produced. Now, again, we'll never be able to prove that, but it's certainly intriguing. And if this is the case, then some of the most revolutionary and groundbreaking works of art that came out of Britain in the 1800s were a direct result of somebody being able to make a different kind of paper. And the technology, the science was helping Turner to create something that maybe he wouldn't even have thought of creating before. So there's lots of examples throughout history, right up to the modern day, of science helping artists to produce a new kind of art. And a number of years ago, I started getting involved in this process to a very minor extent myself when I was contacted by an artist called Andrew Small. Andrew Small is a sculptor, and he was asked to produce a series of landscape sculptures that followed a path that went from the east coast to the west coast of Britain, or rather the west coast to the east coast, a cycle path. And on the eastern coast, he wanted a particular sculpture which marked the end point of the path. And he wanted it to relate to the landscape around it. And he came up with the idea of this very large slab of granite. It's a beautiful piece of stone, positioned in such a way that at exactly the right time of the right day of the year, as the sun rose, it would balance exactly on the top of that lighthouse that you see in the distance there, but only when you stood at this point and looked through the hole. And what he wanted to do is he wanted to connect that to the universe beyond. And so what he asked me to do was work out what the stars would look like if you were standing in that position at that exact time. And if you look very close, you may not be able to see it clearly, but on the picture on the left here, there are tiny little marks on the granite, and they are the star map. And if you stand in that place at that exact time, on I think it's the 21st of April, at that exact moment, the sun is balanced right on the top of that lighthouse. That is matching the positions of the stars at that moment. And this was fun. I was able to do this for him. He went away and created the piece of art, and I thought, well, that was nice. It wasn't a huge amount of work. It didn't really interrupt the day job. Don't worry, Mike, I kept working. But it was quite an interesting thing to do. And then I kind of forgot about it. I haven't even been over there to see this thing in the flesh, as it were. And I just went back to doing my normal work, my education, my research, and so on. But then a few years later, I went to the theatre. I like going to the theatre. I like going to see some slightly unusual kinds of theatre. And I went to see a company called Unlimited Theatre, who do quite unusual things. In particular, one of their artistic directors, a guy called John Spooner, is very interested in science, and he likes to do plays that are about scientific concepts. So the one I went to see was about quantum tunneling. So an entire 1.5 hour play about quantum tunneling and what it meant for relationships. It was brilliant. The science was spot on, but it really helped support the storyline. And so I went to the bar afterwards and got chatting to him because I couldn't resist. And then we talked about what he did. We talked about what I did. And he said, well, actually, he was thinking of developing a new play, but for children this time, where he wanted to go out into space. He wanted to tell the story of the first human mission to Mars. And he wanted to tell it in a way that made 10, 12, 13-year-olds excited about the possibility of the science and the technology that led to that to that journey to Mars. And he asked me if I would like to get involved and give a bit of technical support and advice. So of course I said yes. I couldn't say no to this. Such an opportunity. And it happened. This is a photograph from one of the performances. The two astronauts just as they're heading off towards Mars. And it was a beautiful story because it was all about the challenges, but also the excitement and the aspiration and the dreams. The play starts with one of the astronauts, Stefan on the left there, sitting on the front of the stage and opening an envelope. And on the front of the envelope, it says, "To be opened by me the day before I go to Mars." And this is a letter he wrote to himself when he was 10. And this is the day before he goes to Mars. So from the age of 10, he's wanted to do this. And now he can do. And he's about to head off on this journey. And of course, the people in the audience are 10 and 11. So they're the ones who might be writing that letter to themselves in the future. And it was a great fun play. It was very successful. It toured around the country. It sold out everywhere. And at some of the performances, we did panels afterwards, question and answer panels. This was a child asking lots of questions about black holes. He loved black holes. This was in Leeds. And I sat on a few of these panels, but I think it says a lot about the breadth and impact of this sort of performance when you look at the other members of the panel. So you've got me on the left there. Next to me is a local primary school teacher. Next to him is a social worker. Next to her is Gail. I'll come back to Gail in a minute because she's amazing. Next to Gail is John Spooner, the writer and director. And on the right is the artistic director of the theatre. So we've got quite a range of different skills there. But the one in a way that's most interesting is Gail, because Gail left school at 15. She left school because she got pregnant and the school just wouldn't have a pregnant girl in the school. So she was basically kicked out of school. But she's always wanted to go to space. So she had a baby and she got a job basically in the local supermarket. And in her evenings, while looking after her baby, she started doing her A-levels at evening class. And she got her A-levels in maths and physics. And once she'd done that, still raising her child, in fact, having another one by now, I think, she decided to do a degree, a distance learning degree at the Open University in the UK. So she did a degree in physics part-time while still holding down her job. And then after doing that, she decided to do a PhD, which she did part-time while having another child and holding down her job. And when she'd finished her PhD, she said, right, now I'm ready. Now I can go to space. And so she applied to the astronaut training program at ESA, the European Space Agency. And she got into the last 10, which is astonishing because they have thousands of applications for these things. Now, she didn't get the final pick. That went to Tim Peake, who many of you will have come across. But they were so impressed that they did offer her a job, and she became the head of microgravity training for the astronauts. So she was in charge of the the parabolic flights where the astronauts go up and practice in microgravity, so-called vomit comet. And she did that for a few years, still wanted to go into space herself, but learning lots from doing that. She now runs a nuclear physics lab in Australia, but she's still developing the skills and so on that she needs to go into space. And I believe her. I believe she will do this because she's the kind of person that you spend 5 minutes talking to and you think she can do anything. But she didn't have a particularly good start to this. And so for her to tell her story to this theatre full of 10, 11, 12, 13-year-olds and saying, okay, maybe not every step on the way will go right, but if you really want to do this, you can keep going and you can succeed. And having that story mixed into the play and mixed into the aspirations that came from that really made a difference. We got a lot of feedback from people and from the children there saying that they were thinking about their future in a different way from this. And so this was science helping art, but going beyond just the art itself. To the extent this began to win awards, which we were very proud of. But again, what's interesting here is not just the fact that there are awards, but they're very different awards. It got a charity award for the arts and humanities, and that was to do with the inspiration that it was creating. It got a Sir Arthur Clarke Award for space education, and it got a UK Women in Science and Engineering Award. So these different awards are all looking at different aspects of what this play was able to do. And so that was quite a big step for me to get involved in this sort of science and art together, but it was very inspiring, very exciting, but I also felt that it was really having benefits. It was really making things better for people. And this is another way that I think that science can help art, because it can provide an excitement and an inspiration. And I think that's particularly true of astronomy. We have the awe and the wonder that some sciences don't seem to have. We have these enormous scales. We have huge time scales. Importantly, we have questions that have not been answered, but that people want to know the answer to. You know, is there other life out there? What will happen to the universe? These are questions that people actually do ask themselves, but we haven't answered yet. And as far as artists are concerned, of course, it helps that it looks nice. I mean, here's a lovely picture of the Orion Nebula from the Hubble Space Telescope. And that sort of thing can be quite inspiring for artists. Here's another, I forget which nebula this one is actually. Sure, should know. Sorry about that. But another Hubble Space Telescope image. And, you know, it's not directly inspiring Turner because it's a lot later, but the colors are similar. It has a similar aesthetic effect to it. And these things are inspiring artists. They're taking these images, they're using them in their artwork, they're using them to develop new artwork. So science has done many things over the centuries to help art and to help artists. But is the opposite true? Do artists help science? Now, this seems to be a lot rarer. It's quite rare to come across instances where science research is easier or works in a better way because of input from an artist. But I'm not sure whether it is rarer or it's less obvious, it's more subtle. Even just silly things like when I write a paper and I'm putting a diagram in my paper, I'm influenced by all of the illustrators and artists that I've seen, and that's an influence that's helping me to communicate my science. But doesn't seem to be quite as direct as the way that science can help artists. But there is one area where it is very clearly important, and that's in science communication. In astronomy, we have a big advantage that the interest in astronomy survives from the very youngest to the very oldest. Even when people lose interest in other areas of science as they go through their school career, they might lose interest in chemistry or physics or biology or something like that. They keep their interest in astronomy, and there's a lot of research to back this up. So that's a big advantage for astronomy, but it's also a big responsibility, because we should use that fascination to rekindle that appreciation of science as a whole, and the technology and the maths and the engineering that underlies it. And so a large part of my job is taking the fact that we've got an easy time of it with astronomy when we're talking to people, when we're teaching students, but using that to broaden their horizons to other areas of science, which they may think aren't as interesting, but actually are. And if you're going to have an impact when you're doing this, if you're really going to change people, there's no point talking to people who are already interested. You've got to do what I call preaching to the unconverted. And you can't expect them to come to you. If you want to reach people who are not already interested in science, then you can't set up a lecture and hope that they turn up. There's nothing wrong with setting up a lecture, but the people who come will not be a new audience. There'll be people who are already interested. You can't expect them to come to you. You've got to go to them. And one of my first experiences of really doing this was with artists, and it was involved street theatre. A performance company called the Butlers. They do street performance, very unusual street performance. They dress up as butlers. You can see one of the butlers here. This is Fletcher. And they go to things like the Edinburgh Fringe Festival, and they just offer their services as a butler, hand out business cards. And if anybody wants a butler, they will be their butler for a day or for an hour or something, completely free. And they've done all sorts of things over the years. They've helped people with their shopping. They've taken marriage proposals to people. One wonderful occasion, when I was also battling with them, somebody came along and he was very shy. He was very nervous, and he wanted to buy a really nice pair of shoes. But he was too nervous to go into the sort of shop where you could buy really nice pairs of shoes, where people talk to you about what you want and you try things on. He was just too shy and nervous to do that. So he took a butler, and he didn't need to say anything because the butler did all the talking for him. And he ended up with exactly the pair of shoes he wanted. He wrote to the butlers a couple of years later saying that he wears them pretty much every day. They're still wonderful. And it was one of the most inspiring things he'd ever done at a festival. So the butlers are a really nice way of connecting with people. And I thought it'd be interesting to see whether we could use that to connect with people about science. And so we set up the science butlers. And these are the butlers, but with tea trolleys. And on the tea trolleys, they have the kind of things you would expect a butler to have. This is the breakfast trolley. So it's got eggs and it's got cereals and it's got sugar and it's got tea and so on. And then the butlers take these trolleys into shopping centres or somewhere like that, and they do science with them. And they show people the science. This is actually happening in practice. So we have Fletcher, the butler there, and Marcus and so on. All of them performing to people in a shopping centre in the middle of Liverpool. And it's very safe for the audience because the butlers are a very safe persona. They're not a threatening thing. They're there to serve. And so they drew in lots of people, and they all got interested in the science, and they asked questions, and there was a huge amount of communication going backwards and forwards. It was an incredibly successful event. In that one day, they talked to something like 6,000 people about science as butlers. And so the science butlers performed several times. Eventually, we had to disband them because Fletcher moved house. And he moved to a house with a smaller living room, which didn't have enough room for all the tea trolleys. So we had to disband the science butlers. But the idea worked really well. And that's led on to me thinking about other ways in which I can use art to reach audiences who are not expecting science. One of the things I ended up doing was a residency at the Tate Gallery in Liverpool, a thing called Tate Exchange, where they gave me a room in the middle of a gallery and said, right, do something in there for 5 weeks. And so I brought in aspects of cultural astronomy, looking at the constellations, looking at the names that different cultures have given the constellations and the stories they have behind them. But I also brought in current research. The image you can see in the background there is a feed from the Liverpool telescope. It was the previous night of what the Liverpool telescope on La Palma was doing, what it was looking at, what it saw. And that was repeating on a loop. And people came in, they had a nice look at a Picasso and the Klimt, and then they came around the corner and they talked to me about constellations and telescopes. And it seemed quite natural to be doing that there, but it was something that brought the science to people who had just never seen anything like this before, never had the opportunity to get involved in this. So again, very successful. Quite a lot of work in this particular case. 5 weeks in a gallery takes a lot of effort, but I think it was worth it. And I've done many other things since then, working with different kinds of artists. One of my favorites was with a dance company called IJAD. This started out actually as a health and safety thing, rather strangely. I was approached by a choreographer called Jumana, who runs IJAD. And she's worked with a lot of dancers over the years. And she became increasingly aware that particularly young dancers were spending a lot of time injured, particularly knee injuries and ankle injuries. when she sort of did an informal survey, half of all young dancers are injured at any given time, which is horrendous. And some of them try to work through the injury, which can often compound it, and some of them just can't earn any money for a while. And she started looking at the way they danced, the way they were taught to dance, and she felt it was because they weren't working with gravity, they were fighting against it. And so she wanted to work with a physicist. She came and talked to me about working with dancers to explore how gravity worked through their bodies so that they could adjust the way they danced to work with gravity rather than fight against it. And we had a few sessions with dancers. We talked about center of gravity and we talked about the way gravity worked. And they were able to change a bit how they danced. They were able to think more about using the center of gravity to help them move rather than trying to fight against where it was trying to help them, trying to make them move. But towards the end of the first session, we also started talking about orbits because we were talking about gravity and I'm an astronomer. And they got quite interested in orbits. And two of the dancers said, well, we want to do an orbit. We want to do a planet going around a star. So we started doing that. And one of them was the star, the high mass object, and the other one was the planet. And we talked about, keeping the center of mass sort of between the two. And we talked about the fact that the smaller thing will tend to move faster and it will get faster still when it gets closer to the more massive one and so on. And they were able to reproduce this sort of movement just from those rules, just from the rules we were able to give them. Then the third dancer came back from a tea break and wanted to get involved. And I said, well, you can't. It's only adding one more. It can't be that much more difficult. So we started looking at three bodies and they suddenly realized that the whole thing went berserk. This is known as a three-body problem. It's a big thing in physics and astronomy. But reproducing this just with a few simple rules is not going to be possible. And my reaction to that was, isn't that a shame that we can't do three of them at the same time? Their reaction to that was, that's awesome. We've never come across anything like that before. We've never come across anything where a small change makes such a big difference. Let's do a performance about it. And that evolved into not just a performance, but an educational workshop about gravity, about orbits, and about dance. And this is one of the performances. This was a performance in Manchester, and it comes in three parts. The first part, the audience, usually families, come in, and we give them lots of bits of screwed up paper of the different sizes, and we give them a little sort of seesaw and a round swivel, so a round disc on half a ball, and their job is to balance the bits of paper. And nobody had any problem balancing the two bits of paper on the seesaw, but most people found it very difficult to get two or three things on the swivel, let alone more than that. And then they would go into the performance area and there would be the performance. But as they went in, they were given a role. They could be a planet or they could be a star or something like that. And so during the performance, they were brought into it. They weren't just passively watching this, but at some points they would be the stars and the dancers would orbit around them. And at some points they would be the planets and they'd be orbiting around the dancers. And they'd be given instructions to help them understand how this worked. And that gradually got more and more complex through the dance piece until it got to the end. And the final instruction was just balance the room. And everybody moved so that everything was sort of balanced. And if one of the dancers moved, people would adjust to compensate for that. They were able to just balance the room. The stars were in the right place, balancing the other stars, and the planets were moving around. And then they went back out and they repeated the thing that they did to start with, balancing stuff. And now everybody was able to get 3, 4, 5 things on the little swivel boards. And if I came along and moved one, they would just move one to compensate straight away. They had learnt a huge amount about the way gravity works and the way balance works by taking part in a dance. I've never seen anything like that before. I'd certainly never taken part in anything like that before. And I'm hoping to get back working with IJAD fairly soon. They did a lot of work during lockdown with remote dancing, where they use motion capture to project dancing across the world so that two dancers, different continents, can work together. And we're hoping to use that and bring in some of the ideas of gravity to expand on this even further. So this is a work in progress, but I think it's a very exciting one. But it's still not quite an even balance between the art and the science. This is very much me as a scientist coming in and providing advice and support for the artists, the dancers, the choreographer, and so on, to create their performance. That then can be used to communicate science to an audience, but it's not quite an equal blending of the two. And that's something I want to do. And it's something that a friend of mine wants to do as well, a friend called Gavin Starks. Gavin is a composer. However, his background is also in astronomy. I actually taught him when he was a student. He then went on to do a lot of work with setting up internet companies, in particular charitable ones. He does a lot of work with open data and sharing data and so on. But we've always had this idea that we should do something which brings his artistic side and the scientific side together. And so what we decided to do was look at ways in which we could bring astronomy and sound together. And we've come up with something that we call the Soniverse, looking at the sound of light. And the idea behind this is ostensibly very simple. When we observe the universe, when we try and learn more about the universe, pretty much everything we know, not quite everything, but pretty much everything we know comes about by studying different kinds of light. It might be visible light, it might be X-rays, it might be radio waves, but it's some kind of light, some kind of electromagnetic radiation. However, most of that we can't actually see. We can see the visible bit, that tiny little bit that that makes it through our atmosphere and into our eyeballs. But the X-rays, the infrared, the ultraviolet, the gamma rays, the radio waves, the microwaves, we can't see any of this. So if we want to look at it, we have to take that data and adapt it. This picture is a good example. This picture is of the Crab Nebula, and the greenish bit is visible light. But the reddish bit is infrared light, and the purple bit is X-rays. But they've been colored and stuck together so that we can see them. And that's a fairly standard way of going about representing astronomical images. But people have recently started doing something similar with sound, taking astronomical data, and rather than turning it into a kind of picture, they turn it into a kind of sound. This is called sonification. And there's lots of different ways of doing this. One of the simplest is just to take, for example, a radio signal of a variable object like a pulsar, and then take that radio signal, turn it into an electrical signal, and feed it into a speaker. And then you can listen to the radio signal. And you get things like this. Hopefully you can all hear that. That is the sound of a pulsar spinning around really fast. And I'm going to stop it because it's a really annoying noise. So that's just taking the radio signal and effectively feeding it into a speaker. There's a bit of amplifying and things going on, but it's taking the radio signal and feeding it into a speaker. So rather than looking at a pulsar, you're listening to the pulsar. And that's quite a nice way of doing sonification, but there's other ways you can do it. And when I first started doing work with Gavin, we came up with the idea of exploring three-dimensional data using a combination of images and sounds. This is an example of this, and I'll just pause this. In the top here, what we've got is a radio observation from the ALMA telescope of a pair of colliding galaxies. It's not very high resolution, but it's effectively an image of two galaxies, one here and one there, which are at some point in the future about to collide. But behind each one of those pixels on the image, there isn't just a color, there's an entire spectrum. The microwave spectrum. And this is the spectrum of a particular molecular line. So it's telling us a little bit of information about how that molecule is moving around. Basically, it's talking about the Doppler shift. So if you've got a red bit here, what that's doing is it's saying that the light from that molecule at that particular part of this galaxy is being red shifted. So it's moving away from us. If it's green, it's probably staying put relative to us. And if it's blue shifted, so it's moving towards us. So you can get some idea of what's going on by looking at this. But we came up with the idea of having this picture, but as you moved your mouse around it, it would take the spectrum behind that pixel and take the shape of that spectrum and turn it into sound. So the redder part of the spectrum would be lower pitch, and the bluer part of the spectrum would be higher pitch. And so we can move the mouse around and listen to it. Hopefully you can hear high-pitched bits and low-pitched bits as the mouse moves around. And there's a lot more tonal variation than you can get just by looking at the colors. So I was interested in this because it's a way for me to explore data, three-dimensional complicated data, in a new way, using an extra sense, not just my sight. Gavin was interested in this because this is a new instrument. And he actually uses this in some of his performances where he comes along and rather than, playing a clarinet or a keyboard or something like that, he will bring this up and he will play this galaxy and he will use those tones as part of his composition. It's not to everybody's taste, but I quite like it. So this got us thinking about unusual and innovative ways of taking astronomical information and turning it into sound. But it felt slightly contrived. We liked it, and I'm going to produce some more of these things with other galaxies for him, but it felt a little bit contrived. It didn't feel like it was telling us as much as we could learn about the science, which is where we came across the idea of the soniverse. And the soniverse is going back to first principles and saying, okay, what if we had a universe, a bit like our own universe, but instead of things making light, they made sound. So instead of having photons traveling through the universe, we have things that we've decided to call sonons. Can we take the laws of physics? I say we, can I take the laws of physics and rewrite them from first principles so that they produce sound instead of light, and then build a complete model, a computer model of these new laws of physics, create a soniverse, put astronomical objects in it, and see what it sounds like, see how it evolves. This has a sort of history in the way music has evolved. If you go back a few hundred years and look at the evolution of Western music, particularly European music, there's been a progression of increasing complexity. So you go back to the 1400s and it's monophonic chant, the kind of Gregorian chants that you may have come across. And then they developed into harmonies and polyphony, and you started getting madrigals in the Baroque period. And then when you got to Bach and Mozart, they started having more complex forms, and they talked about refinement of the harmonies. When you get to Beethoven and Wagner and the sort of symphonic and operatic things, then again, it's more complex, and they're talking about the harmonies in terms of ratios and other mathematical terms. And those mathematical terms start sticking with the description of music. So when you get to the early 20th century and the middle 20th century, you've got people like Messiaen, Philip Glass, and they talk about their music in terms of mathematical concepts like prime numbers. And they talk about dissonance as well as harmony. And then you've got people like Trevor Richart and John Cage, and they use phrases like mass, grain, texture, lattice, mathematical terms which are starting to get more complex. And Gavin thinks that as our maths has progressed, so will the music. And the next progression in music, in sort of Western classical music, people will be talking about things like curvature, gravitation, manifolds, spin, the mathematical terms for describing complex universes. And so he wants to bring those ideas into the soniverse so that we can hear the mathematics behind what's going on. So there's lots of reasons why we want to do this. I'm interested in actually hearing astronomical phenomena. Can I hear redshift? Can I hear stellar evolution? What does dark energy do to the sound of the universe? That sort of thing. Gavin wants to use this as a compositional tool rather than writing a set of notes on a piece of paper for an instrument. What he wants to do is decide on the parameters of a soniverse. How fast is the speed of sound? How long does the soniverse last? How dense is it? All these sorts of things. And then just let that soniverse evolve and then use the sounds it creates as his music and maybe mix together different soniverses. So he's using it as a compositional tool and an instrument. Another thing I'm quite interested in is just a new way of playing with the universe. Many of you will have smartphones with apps on where you can point them at the sky and they tell you what you're looking at. But it might be quite interesting to point it at the sky and hear what you're looking at. as extra information, but also perhaps to help those who are visually impaired and can't see those apps very well, particularly in the dark. So that's quite fun. The main reason, though, is because we think we can, and nobody's ever done it before, and that's fun. This is not something that is easy. It's not something that I consider to be a core part of my job, but it is something that I'm thoroughly enjoying. I'm going to go down to London, where Gavin lives, in a couple of weeks' time. We're going to spend a weekend just talking about what we do next in this, because we've still got a long way to go. We've made some progress. We've got the beginnings of our cosmological model for our soniverse, and this is a little tool I've written for Gavin where he can play around with the parameters of the soniverse, its expansion rate, its density, and so on, and he can see how that affects the sound as it travels through it. But the sound that we're generating in the distant parts of our soniverse are just optical observations of the real universe turned into sound, quasars in this case. So there's still things to go. We've got the cosmological model, but we need next the emission mechanisms. What is the physics that generates sound? What's the equivalent of a black body? The glow that you get because things are at a particular temperature, which makes stars glow. What's the sound equivalent of an absorption or emission line that you get in the spectrum of a star, and so on. And this has led to some quite interesting challenges. One of the things I've realized, for example, is I've had to reinvent the ether. For those of you who haven't come across this, the ether was this idea mainly in the late 18th, 19th centuries, that because sound waves needed a medium to travel, if light was waves, it also needed a medium to travel through. And they came up with this concept of the ether, which is what light traveled through. It's what vibrated. We now know that, of course, the photons of light carry their own substance with them, in effect, so you don't need an ether. But if we're going to have a soniverse, if we're going to hear anything, then there's got to be a medium for the sound to travel through. So I've got to fill my soniverse with some sort of material. And at first that annoyed me because it seemed a little bit contrived. But then I started thinking about what the properties of this material would have to be. And of course, it would have to have a certain amount of mass. Otherwise, there's nothing to carry the energy. And as soon as you've got mass, then it affects gravity, and it is affected by gravity. And I suddenly realized that this is going to move around in a way which is going to be very similar to dark matter. So my soniverse automatically has dark matter. It doesn't have to be a new kind of particle, it just has it in it. So that turned from being annoying into quite a nice thing. But there's still a long way to go. One of the most important things I've learned about this is I don't understand physics. I thought I did. I did my degree in physics, and then I've been doing research into physics for years. And then I sat down and thought, well, actually, how does light happen? And I didn't really know. Every time I thought I'd got to the lowest level, there was another level below that. And so I'm really having to understand physics better, which is very exciting for me, although it was a little bit embarrassing when I realized how ignorant I actually was. But there's other things that are different with sound. We don't really talk about amplitude of light. We don't talk about amplitude of photons. But sound amplitude is a more important thing. So how do we get that concept in, and so on? So there's lots of challenges to this. We're in the very early stages, but I think it's going to be exciting. I think it's going to lead to something where the art and the science come together to create something genuinely new. But we're not really the first people to ever try and do something like this. Even going back as far as Kepler, the idea that sound could be used to explore aspects of the universe was important to him as well. Kepler was a deeply religious man, and he felt that the universe should, at some level, be perfect. And so when he was looking at the orbits of the planets and he was starting to come up with his ideas of elliptical orbits and so on, he wanted to try and find some sort of underlying harmony behind that. And one of the ways he did this was to try to use sound. In his Harmony of the Spheres from 1691, he associated musical scales, musical patterns with each of the planets and the stars beyond them. And what he tried to do was he would take those musical patterns and he would play them on a keyboard, harpsichord or equivalent, in time with the orbits of those planets and see what it sounded like. What he found is it sounds awful because they don't have that underlying harmony, but he was using sound to explore that. And we're sort of doing the same sort of thing. But we've now got the computer technology and the understanding of the universe to go many layers beyond what Kepler was able to do. And maybe we will find those underlying harmonies. Maybe we will find aesthetic appeal in the universe, as well as information and knowledge. Which brings me back to C.P. Snow again and his Two Cultures report. One of his other quotes from this report, some of which is a great read, he says, there are two polar groups. At one pole, we have the literary intellectuals, and at the other, the scientists, and as the most representative, the physical scientists. Between the two, a gulf of mutual incomprehension. Now, that wasn't entirely true then, and it's not entirely true now, but there is a certain amount of that. But what I've learned over the years of working with artists and exploring art as a way of exploring science is that actually there's a lot more we've got in common than you might think. One of the most important is, whether you're an artist or a scientist, the fundamental thing you're doing is asking what if. Artists ask themselves what if in order to generate their art. And we do that because we want to change how we look at the world. We want to change how others look at the world and the universe around them. And they're both using imagination. Some people think that scientists have no imagination, but you cannot do science without imagination. You have to imagine a different way of understanding the universe before you can try and explore that scientifically. So there are things that we have in common. There are ways of starting conversations between the two of us. But there are also differences. And I think one of the most important differences comes from the way we choose to constrain ourselves. Art is constrained. If it's not constrained, it's completely free for all and you don't get anything concrete out of it. So art has to be constrained by what the artist wants to achieve. It might be that they want to achieve a particular emotion in the viewer. It might be that they want to achieve a particular way of thinking in their audience. But they are still constrained by what they want to achieve. Whereas science, crudely, is constrained by reality. You ask what if, you go away and test that what if, and it doesn't match reality, then that what if was wrong, and you try and think of a better what if. And so those constraints are actually quite different, and that does affect the way that we do our science or our art. But it doesn't prevent us having those conversations and working together. And what it always comes down to is, what questions are we asking? And can we ask those questions of each other? And so I'll bring that to a halt. I hope you found some of that interesting and thought-provoking. I will leave the big question mark up there because now I think it is time for you to ask me questions. But I just want to finish by saying that this is something that I'm very new to. I'm not an artist by background. And so I'm learning this as I go along, but I'm finding that the more I learn about the way artists work, the more that helps me to understand how I do science. And maybe it's going to help me to understand how I do my science better. So I strongly recommend anybody who has the opportunity to work with artists, to talk to artists, to argue with artists. You will learn a huge amount about art, but you will also learn a huge amount about science as well. Thank you very much.
Well, thank you, Andy, for that superb talk. Very thought-provoking in so many ways. And not very many people who've gone from doing a PhD on mapping the large-scale structure of the universe to inventing their own universe. So if people have got questions, I can see Steve's got a question.
Oh, I better bring up the chat so I can't see that. Let's have a look. Yeah.
So
Hi,
Steve.
Andy. Yes. Hi, Andy.
Hi, Steve.
Hi. Oh, that was fascinating. Loved it. And thank you. Big kudos to you. And I really compliment you and everything you're doing. I'm wondering how you envision science fiction, like Arthur C. Clarke science fiction. Do you think that sort of fills in partly a gap between art and science?
I think it does, yes. I think it's bringing together good aspects of both of them to create something that's a bit new. I do tend to find, though, that if you like the kind of the hard science, Arthur C. Clarke kind of science fiction, tends to appeal to people who also already like science.
Right. Okay.
So what they like about it is it's allowing them to explore a bit of the science they're already interested, as well as getting a good story.
Okay.
Whereas some of the more extreme science fiction, some of the more speculative end of things, the sort of Ian Banks kind of exploratory stuff, that has a broader appeal. Because scientists do find it interesting, even if we occasionally go, what, really? But it's also appealing to people who just like the breadth of the imagination to it. So I don't think there is a single box that science fiction fits in this art science thing. I think it has
No,
very
it
large
doesn't.
spread.
Yes, it's a wide spectrum. Yes.
Yeah.
Yeah, that's okay. Thank you.
Thank you.
Okay. Did Francis have a hand up at one point, or?
No, sorry, that was just me giving a round of applause.
Thank you.
Very interesting talk. Thank you so much.
Thank you.
Andy, can I ask you a question then?
Of course you
can. Sort of chair's prerogative. When I was in Thailand last week, in the planetarium there, they were showing some stuff they were doing with visually impaired people, and they were doing 3D printing of spheres and so on, and putting star patterns on those, and then they do the presentation to the public, but they could follow what was going on by feeling. But you touched on using some of what you're doing for the visually impaired. Is that something that you are working on, or is it? It's got some potential though,
yes,
hasn't it? Yeah.
I've started doing a bit of that. Haven't got very far yet, because I need to understand the problem more. There's no point trying to solve the problem if you're just sort of leaping in and think, I can solve this, when you don't actually understand what it is. So I need to understand the problem more. I need to work with more visually impaired people. Certainly the touch aspect is very important, and there's a lot of very good projects going on. There's one run from Portsmouth called the Tactile Universe, which is superb. And we have started, I did briefly talk to them about the idea of bringing together the work that we're doing with sonifying the data cubes, so the ALMA data and the sort of spectra, with their 3D printing, so that when somebody got hold of the 3D printer, we could use devices which work out where fingers are. So as they touched the 3D printed galaxy or something like that, it would then play them the spectrum behind it, so that they're also getting the three-dimensional data. So that's one thing that we have started looking at. The only problem is nearly all of them sound awful, and it's actually quite annoying. So we have to find a way of doing it that's not deeply annoying to the people who are actually having to listen to this stuff. But yes, certainly it is an area I want to work more with. And there's a couple of schools for the visually impaired that I'm making contact with at the moment, and seeing if we can work with them to find out what their biggest challenges are in connecting with astronomy, and whether we can use both touch but also sound to help them explore those. So yes, hoping to go more into that direction.
Good. Do you have any other questions? Okay. You're getting some really nice comments here.
I
Andy,
am.
very
Thank you
well
all.
deserved. And it's quite weird, really, because Andy and I are sitting within about 5 miles of each other on a peninsula called the Wirral in the UK, and we're getting comments here from South Africa and all over the place. So this just it's one of the few benefits of the pandemic, was the use of Zoom for these things. But it really brings the world together a little bit, and that's always a good thing.
Change your background to make you feel more at home, Mike.
Oh, that's very good. Right. Okay. There's a question from Dr. Schipper, which is,
yes.
Can you briefly summarize how you encode the red and blue shifts?
Yes, so this is in the ALMA data. It's actually very simple. I took the spectrum that was behind that pixel, and the reddest end of the spectrum, I made a frequency of about 40 hertz, and the bluest end of the spectrum, I made a frequency of about 2000 hertz, and I just mapped them right the way across. That gives you a power spectrum of the sound, and you just take that power spectrum, do an inverse fast Fourier transform, and bingo, you get sound. So in many ways, it's quite a simple thing to do, but I'm arbitrarily choosing the lower and upper frequency range. So I could make them wider and you get a bigger pitch variation. I could make them narrower and you'd get a smaller pitch variation. So that's where the slightly arbitrary bit comes into it. Does that answer the question?
Oh, yes, yes, yes. Thank you very much.
Excellent. Oh,
Yeah. Do you want to answer that from Ryan?
yeah, the easiest way is probably on Twitter, even though it's dreadful. I'm AstroNDN on Twitter. So that's probably the easiest way of getting hold of me.
This is being recorded, so the recording will be on the ASB's website afterwards, as long as technically everything goes okay. There's a comment from Just.
Oh, yes, thank you.
Yeah.
Oh,
Ask
Deborah
another
and Steve.
question from
Yeah,
Deborah
go
and
on.
Steve. Yeah, go on.
Sorry. Okay. Hi, Andy, again. It's not a question, actually, because in what part of my life I was a dancer and also an astronomer. So I love the melding of the arts. And as you were playing, well, not playing, as you were moving the cursor around the interacting galaxies and hearing the different sounds, I just immediately, my mind went to a kid's interaction with dancers on stage who are wearing blue, green, and red suits. And as they move the cursor around, the dancers would have to move forward or backward or across the stage. It came to mind. I just put it out there as a suggestion.
I like that. I'm going to have to talk to Jemana about that one and see how she reacts. Yes, definitely.
Yeah. No,
If she goes for it, I'll make sure you get a credit.
Oh, no, that's okay. It just came to mind. I thought it'd be great interaction with the kids.
That's lovely. Yes,
Yeah.
definitely. Yes.
It would be quite crazy, it would be improvisation and anyway, but yes. That's all. Thank you.
Thank you. No, I like that. Thank you.
Yeah.
Yeah.
And a suggestion from Prof. Medici, which is about extending this to science and sport.
Absolutely. Yeah.
Yeah.
Yes, definitely. And we have a very nice sports science department here at John Moores University, so I will be talking to them about this sort of thing as well. Definitely. Yeah.
Okay. If there are no other questions, we'd probably better call a halt this evening, although I think we could have carried on for quite a long time. And just say thanks again to Andy. Thanks to everybody for attending. There's another talk at the ASB in a month's time, and that will be by Joran Ulusoy, who's a lecturer at Buist on some aspect of stellar astronomy of the stars. So without further ado, thanks again, Andy. Thanks, everybody. We will make the recording available on the website, and happy 2023 to everyone. So thank you.
Thank you very much, Andy. That was fascinating.
See you soon. Bye.
Yeah.